Let's give a big hand for Mathias, who's going to talk about agile experiments in machine learning.
Can everybody hear me all right? Good, looks like it's working. So yeah, I'm going to be talking about Agile and machine learning. So it's .NET French, so these are definitely both kind of French topics. My name is Mathias Brandewinder. You can find me on Twitter. My core interest is F# and machine learning. You can, of course, you got it from the accent. I'm coming from San Francisco. And so the reason, the source for this talk was recently, I did a machine learning competition with a couple of friends. And so the team was like 6 or 7 people. They were all very qualified, very good software engineers. And what happened was we started working, and like 3 weeks later, we had a repository in GitHub, and the repository was a complete mess. And so this got me a bit thinking, because I thought, how come like you put a team of highly qualified people, and within 2 weeks, everybody's doing all the wrong things, and people did things they would never do otherwise. And so this got me thinking about how is machine learning maybe different from regular code writing, and how would you what type of process would you do if you had a machine learning team? How is writing code for machine learning different from regular code? And how maybe also things different when you're using F# for machine learning? So this is where this talk is coming from, is like starting from something which didn't work out, how we got into a different process for machine learning using a statically typed functional, and like maybe some lessons you could learn out of this. The whole repository for the competition is also on GitHub. I'll put the link afterwards in a place where you can get it. So first I'm going to start by explaining a bit what the competition was about. So the competition was organized by Kaggle, and the client was Home Depot. So I'm assuming you all know Home Depot. This is where you go if you want paint, if you want showers, if you want axe murder tools, all these things. So, and the team was a bunch of people. I just want to give credit to 2 people in particular, Jamie Dixon and Taylor Wood, who are the 2 main contributors besides me on the project. And we did pretty well. So there were like over 2,000 teams, and we ended up like 122. So we didn't make any money out of this, but like we got into like the 5% range out of 2,000 people, which I think is pretty decent. So what was the problem about? On the first slide I had, we had like a box, which is a search box on Home Depot, and so if you go to Home Depot, like most websites, you type in something which you're interested in, and what will come back is a bunch of products which are propositions by Home Depot. So in this case, you have a search which could be like, I want a 6-inch damper, whatever that means, and what comes back is a product with a description, a Batic door energy conservation product, blah, blah, blah. So this is what the website suggests. And the question was, is the recommendation Home Depot is giving you any good? So to address that question, what we had was a data set. And the data set was just a whole set of queries and results. So in this case, for instance, somebody wanted an L bracket. The result was a Simpson strong tie 12 gauge angle. And then you have like a third thing, which is a rating. So they asked people to simply look at these and rate it from 1 to 3. 1 is like what came back is absolutely terrible. 3 is awesome. 2 is average. And so this is what you have. Like you have a long history of like searches and results. And our goal was to figure out if yes or no. Yeah, that's the problem we're trying to solve. The problem we're trying to solve is like given a search, what you typed in the box, given the product that came back, what you're trying to do is you're trying to predict like how relevant this is. So it's like you're trying to predict, is this 1 terrible, is this 3 awesome, or is this 2 an average recommendation? That was the whole goal of the competition. The exact structure of it was we had like 70,000 training examples, so like not big data, but like a nice data set. And the goal was to predict on 20,000 search and prediction pairs, predict all of these and get the smallest possible error on that data set. So this is what this is kind of the general setup for the competition. So to do this, this was a machine learning competition, so obviously we used machine learning. And so before starting with what we did, I'm going to start with what we didn't do to try to explain a bit why machine learning might be a bit different from writing regular code. So if I put my software engineer hat on and not my machine learning hat on, I could really write a solution to the problem, which is going to take me like a good 30 seconds. So this is like a possible F# solution. What I could do, I could say I'm going to write a domain model, and my domain model is what I have observations. An observation is a search string, and is a product string. And what I'm trying to do is I'm trying to write a function which is going to predict how good or how bad the result is. And one possible solution would be predict. if you give me an observation, I'm going to predict every single time 2 as a rating. If it's good, if it's bad, it doesn't matter, I'm going to give you 2. And so there are a couple of points here. So the good thing is that in 1 minute I can write a model which works. Now if you look at this, you are probably thinking yes, but this is terrible. And I would agree. But this is kind of the point. So obviously we have a solution which works. We have a solution which is entirely correct, and it's completely missing the boat. So where is this missing the boat? The domain is actually completely trivial. If you think about it, I could write unit tests on this model I wrote, but this would be entirely missing the mark. What matters here is not really whether the domain model is correct. So the question is, which is really typically what you do when you write a line of business application. Somebody tells you you need to write this feature. Once it's correct, you move on with your life. Here, if I do this, I have code which is perfectly correct and which is completely missing the boat on what we're trying to do. So the question here is if what we're not trying to do is write that type of code, what is it that we're trying to do? And so what we're trying to do is we're not trying to write one piece of feature which is going to be done. What we want to do is we want to write a function predict, and we're going to, instead of finishing that feature once, we're going to change that function over and over and over and over again. And what we're trying to do when we change the function is we're trying to be creative, and we're trying to find a function which fits the data better. So we're not going to have a feature which is done or not done. We have something where we try to be progressively better at making predictions. So the point here is instead, on a line of business application, typically you have many features and you do them once at a time. Here we have one feature only. That feature will never be done. I cannot say close finish. It's going to be a bit better and a bit better. And we're actually going to potentially write many, many, many versions of the domain. So this is a space which is pretty different from what you're trying to do typically. So one word, and so part of the point here is if we are doing something which is different from a typical line of business application with tests, then chances are any process you use typically is also not going to work. Usually processes are meant with a certain idea of how the code should look like. So the question is if we're doing something which is not typical code, what are we doing? And can we actually find a model for what we're doing which is more relevant to the problem we're trying to solve? So I brought a word on the previous slide which was experiments. What we're really doing here is we're conducting many experiments and trying to improve a model. And so if we take that word in, we have a bit of a framework on what we're trying to do. And so a closer model for what we're trying to do is actually coming maybe from the community of researchers, physicists, scientists. And so if I'm trying to conduct an experiment, let's think a bit about what this means. Usually it means first I care about something. So something can be many things. In this case, it could be predicting whether the moon will be full. It could be predicting if my rocket is going to hit the moon, all these things. I care about a phenomenon. What we want to do when we conduct an experiment is we have a phenomenon, and what we have is we have an observation. We're trying to build a model which is going to give us a prediction. If I drop this rock, that rock will fall at that speed. This is actually not exactly what we're trying to do. What we're trying to do is we're trying to build a model where we take an observation. That observation, this is a rock, we're actually going to extract data out of it. For instance, out of the rock, I will extract x1, that's the weight, x2, that's the speed, x3, that's... So I'm really trying to transform something into a set of numbers. My model, which will be my prediction, is really a function. So I'm going to pass this input into a function f, which is going to give me a number, which is what I care about predicting. Will the moon be full? Is the speed of the rock 3.5 feet per second? Something like that. So we are extracting data, passing it into a function, and predicting a number. So this is really, what we're really doing here is we are formulating mathematically out of the things I see out of in the world. I represent this as maybe the planets are formulating a circle under the sun, or maybe a circle around the Earth. So this is what we're doing. We're formulating a model here. Our next step is now that we have an idea, and this is maybe how the world works, what we have available is a collection of observations. I have a long history of dropping rocks and measuring how fast they go. I have a history of planets circling around the Earth, or the sun or whatever. So we have observations and results. And what we're going to do is we're going to take that data, and we're going to calibrate it. So the chart on the left is showing the most obvious calibration you could do, which is maybe you have a straight line, and you're trying to say if the world behaves the way I think, with the data I have, this is the best data which would fit my model. And once you have calibration, you're not entirely done. So this is a great quote by a physicist called Niels Bohr, which stated something which might be obvious, but which is still true, is like predictions is very difficult, especially if it's about the future. And so the reason this is interesting is like in this case, if you're a physicist, is like the fact that you have calibrated your model is really not finished. What you're really trying to do is you're trying to construct a model which is actually going to produce predictions tomorrow on data it has never seen. Like reproducing the past is not very interesting. What you're trying to do is to predict the future. And so this is where you're going to validate, is that you're going to say, I think the moon is circling around the Earth with this type of a model, and then you're going, given this, you should be able to predict tomorrow the moon will be full, and if it's not, then your model is incorrect. If it's not, if it's correct, then your model is probably right, and it becomes the best truth until you find a better model, or you find a counterexample. Good. So this is a super simplified view on how science works. But this is kind of the overall process we followed here. If you're a scientist, it's like first you're going to formulate a model. Like, I think this is how the world works. You make it into a mathematical model, then you calibrate it. So you're going to take data, and you're going to look at, if I think the model is this way, this is how the numbers should look like. And then you're going to validate it by just looking at data, by making predictions and seeing if the predictions actually work. And so this is actually exactly what machine learning people do. So what you're doing you can just take pretty much step by step this workflow and translate it into machine learning terms. So formulating a model is what people call extracting features. Like you have your data set. For instance, in our case, you have like we have the Home Depot searches, and we're trying to transform this into a set of numbers to predict another number. So maybe the features could be something like, I think the length of the query matters, I think the number of characters matters, I think how it matches to the result matters. So we're transforming it into numbers. Then we're doing calibration. So this is what people in machine learning call learning. We have these numbers in input, that number in output. We're passing it to a learning algorithm, and we're trying to match as closely as possible the data, the input to the output. And finally, we're going to validate. So we have this is typically called cross-validation. We keep like a bit of the data set on the side, and we're going to see if actually the model matches the data we have. So the point here is, the recap here is that the two processes are fairly different. When you're writing traditional software, you're building incrementally discrete features and adding them one to one to one to one until you're done. In machine learning, you don't really do that. What you do is you're trying to create many experiments to get better and better and better at predicting something. And so in that frame, like the traditional process is also probably not going to work very well, which is what explains how in 3 weeks we had a repository which was looking like complete crap. So this is a bit of context on machine learning. Now, what I want to talk about a bit is like, there is the theory and then there is the practice. So in theory, practice and theory are the same. In practice, they are not quite the same. So I wanted to talk a bit about how actually scripts in machine learning look like. So first, typically people in machine learning use scripts, and your prototypical script will look along these lines. First step is I'm going to load data because I need data to make predictions. Then I'm going to extract features. So what I described before is like out of the data, I'm going to transform it into numbers. Next step is I'm going to use an algorithm to actually learn from the data to the output. And finally, I'm going to check how good and bad the model is by looking at another data set and see if yes or no the predictions are good. So I'm going now to move to show you some actual code. So the code I'm going to show is not an actual real script, but let's say it's a slightly simplified version of the scripts we have been writing in the first weeks of the project. And so imagine for a minute that I'm going to make a hypothesis, and so what I'm trying to predict is like, I have again like search terms, I have product descriptions, and I have like how good or bad the match was. So maybe I'm going to assume that the length of the search matters and the length of the product tile matters, and I'm going to see if I take these numbers, can I actually make some reasonable predictions about yes or no, was the recommendation any good? So first step, as I said, loading data. So this is going to be a bit of F#. Like I'm going to simply take my data set, which is, of course is a CSV file, and I'm going to load it with a CSV provider. So this is done like one line, so that's fine. Now I have my data in memory. Like the second part, which is getting a bit more interesting, is like now I want to extract features. So if I want to extract features, out of my sample, I get rows, which are like rows of data from my data set. For each of them, I'm going to extract two things. The output, that's the relevance, like from 1 to 3, was this good or was it bad? And the features. And so the features are going to be something like this. Here for a row, I'm going to say I care about the search term's length, like how long was the search, and how long was the title. By the way, the model is pretty stupid, but it's more as an illustration of the general process. So here I'm extracting for each row the output I'm trying to match, and the values I'm going to use, the features which I'm going to use to try to predict it. So let me try to run this. And if I run this now in my script, what I'm going to get is I'm going to get some data. So the output is like a big vector of relevance, like from 1 to 3, and the input is going to be for each search, like the numbers I can use. Fine. So next step is where things start to get a bit earlier. So now what I want is I want to learn a model which is going to use that data to predict something. So here I'm going to use a library. It doesn't really matter. I could use many libraries. I could use many models. I'm going to use one which is called the logistic regression. The details are not hugely important. So what this is going to do is simply take the input and try to fit it to the output. And now is where things start to get a bit earlier, because like every algorithm has a slightly different views of the world. And so, for instance, like if you remember, the output we have is a number between 1 and 3. Unfortunately, like a logistic regression is expecting outputs to be from 0 to 1. So now I need to start tweaking the data to fit with the algorithm. And here I'm going to take the output and move it from 1 to 3 to 0 to 1. So I'm going to do that here. Did I pass it in? Yes, I did. And now I'm going to also use my logistic regression. I'm building a bit of a learning model here. So that learning model is going to take that model and iteratively try to get better and better and better at predicting. So I'm going to run this. And I'm going to run this on my model. And now the last step I need, so now I have a model. I'm not finished. Last step is I need to check if it's good or bad. Simple. I'm going to take my data again. And for each of the values I have, I'm going to again extract features. And for each of the features I extract, like the title length and the product title length, I'm going to pass it to the model I did, make a prediction, and I'm going to check essentially, is the prediction close or not close to the number I was trying to find. So I'm going to run this, and now I'm going to make a couple of comments. So the good thing here is that, so this is pretty much what everybody's doing in machine learning, writing scripts, adding, and writing something which looks like that. The thing which is nice is like in 80 lines, so I have a model which is terrible, but like it took me 80 lines of code to get a model which works, which predicts something. That's not too bad. The thing which is not great is like if you take back your software engineering hat, is you can probably see a couple of things which smell like trouble in the long term. And the thing which smell like trouble are along these lines. What I'm really trying to do is I'm trying to create many experiments. And so if I'm trying to create many experiments, I'm going to do a couple of things. I'm going to add features, I'm going to remove features, I'm probably going to try to swap out algorithms, put different algorithms into my model. And if you look at the way my script is written right now, it's going to be extremely difficult to do. Because if I want to add a feature or remove a feature, this is what I'm going to have to do. I'm going to have to go here, and I'm going to have to start changing what's happening in this array here. Like I'm going to maybe take search terms, take matching terms. So I'm going to add code in this. And this is really hard to spot. On top of that is like I have massive code duplication here. I'm doing exactly the same thing on the validation step. So you can see already like code duplication, so change is not going to be fun. I have also the whole part where I'm messaging the data to pass it into the algorithm. If I change algorithms, I'm going to have like lots of small things to tweak. So any change I have to do is going to be very likely full of bugs. And this is exactly what happened. The other thing, which is more broadly a problem, is if you come from a DDD background, is you probably care about something like ubiquitous language, where if you describe a problem, the code should probably look like the problem you're describing. And here, everything I told you so far was I'm trying to do experiments, I have features, I have this, I have that, and none of that vocabulary is showing up in my script. That's also a very big smell. So this is where, I think this is why we started to run into a wall and why our scripts and our process was just like going downhill very fast. So now I'm going to go back to what we did to address this. So the problems are like how to track features, how to swap algorithms, and the code doesn't reflect what we're trying to do. So this is really wasteful, because like on one hand we're writing scripts fast, on the other hand we're going to spend a lot of time on like loading data, on fixing features and all of this, and this is not focused on the place where we're trying to add value, which is creating experiments. So to avoid that, the take was, let's see if we can actually build flexibility in our process on the places where we're going to have lots of change and automate everything else. So the strategy we followed was use types, because like, that's what F# people do, automate everything that doesn't change, and make the creation of features as easy as possible. And this was amazingly or surprisingly simple. This is a bit of F# code, and this is like very close to what we ended up doing. So what we did was, if we have observations, like we should probably have something which is an observation, which is a search string and a product string. What we're trying to predict is a relevance. And then if I have this, what I'm really trying to do is to create a type which is a predictor, and a predictor is a model, which will take an observation and give me back a relevance. That's a model. And this looks exactly like the way I would describe it in English. Then I have a feature. A feature is not an array of floats. A feature is a function which is going to take an observation and give me out a number. That's also exactly how I described it in English. Finally, I have examples I can learn from, and an example is an observation, and an observation where I know also what the relevance was. So was it a 1, was it a 2, was it a 3? And in that frame, a model should be as simple as a collection of features, and learning should be something which takes in a model, like a collection of features, takes in a collection of examples, and from that collection of examples is going to learn a predictor. And if you look at the repository I have, this is exactly how it is. And arguably, in like 20 lines of code, I have a framework which works on pretty much every machine learning problem possible. This is nice because out of this, now I can start solving my problems. I know that a feature is something which will take an observation and give me back a float, so I can start to write a catalog of features. My catalog of features will be, for instance, search length is a feature, product length is a feature, all of these are functions, and I can put them nicely in a separate file. And I can version them, I can share them with the team, I can share them across different models. And now I can start to build something which is an experiment, which is what I was after. And so an experiment will be simply load some data, so that's shared code like removed out of this because it's not useful, but a model will be, in this model, I will take search length, product title, matching words. So this is like very readable. If I look at this, I know exactly what, it's not hidden in arrays and all of this. I can see my model was using all these features, and now I can pass it to a particular learning algorithm, and I will get like a quality by evaluating against the data I have. So maybe I hear that architects like boxes, so I put like maybe a more boxy architecture version of this. So what we really did was using types, we split a bit the code this way. The idea was like we want to have reusable pieces and a stable workflow. So the stable workflow is I will use the same data all the time. What I want is I want to build an experiment where I'm going to say I want to use feature 1, feature 3, and feature 7, but not feature 2. And I want to use one of the possible algorithms, put this in a script, and then run it into validation. It will be always the same. And so this is what I got with this. And what I extracted out was I created types of features so that I can now have a catalog of features which are completely separate. So I can plug them from the shelf and put them in my experiment. Algorithms with a bit of adapters, I can also say, actually, instead of algorithm 2, I want to plug algorithm 1. So now I'm exactly where I want. I can use the same workflow all the time, and I can create very easily experiments, do variations, and see immediately what the results are, or should be. So I'm actually going to show you like super quickly how the code looks like to show you that I'm not lying. Like this is really what we did. So I have like I have a better version now, but like the way it looked, like I have a bit of loading code here. But like my experiments look exactly like this. I have a model. My model is like the features I want. I'm creating a model here, and I'm simply computing the quality here. If you look at, so essentially I reduced like to 10 lines what took me like 80 lines before, and this is extremely clean at that point. So, so this is what we did, and this is the goal we're trying to achieve is achieved. Did it work? Unfortunately, so as a data scientist, I wanted to bring a chart and see how it worked, but like the short version is like it worked really well. Because what happened was we started with a dirty script. It worked very well for 3 weeks. After 3 weeks, it ground to a halt. Then we started refactoring to the model I described, so everything died for 2 weeks, like where we got nothing done, and after that we started to ship pretty much like new models like every hour, and like at that point like the quality of our model went up, and so it really paid off. It worked really nicely. So the recap here is what we did was we have a nice statically typed language in F#, so what we did is like we use types to model the domain so that we would actually have a language in our scripts which was reflecting exactly what we were trying to do. And we separated the code. In the code we separated things so that we could actually easily add and remove features, easily swap algorithms, and have a common workflow across all the experiments. So conclusion. There are two conclusions here. One of them, so this is something which I've been a bit obsessing about. I really like machine learning, like this is what I do. But like this was an interesting case, I think, because I hear lots of discussions about process and arguments like, is Lean better than Waterfall? Is it better than Scrum? As like in the end, is like there is no perfect process. Like the process should really reflect what you're trying to do. And here it was an interesting case because we're doing something which was obviously not regular code. And so this forced us to look at the process and see what worked and didn't. So first point is like, don't be religious about the process you're following, and more think about why is it that you're following a process, and find out like where you're wasting energy in your process. Try to remove these problems and build flexibility where you want to have lots of changes or where lots of changes are going to happen, and automate everything which you can repeat otherwise. The second part, which is interesting to me, is so in the machine learning community, people typically use dynamic languages. Most people do, like they would use R, they would use Python and all these things, and that's nice, but I really like F# and static types, and what this gives me is a couple of things. Like arguably, from everything I have seen, like first, the scripts we produced are like amazingly clean, and so that's nice. It's clean because I have pipelines, I have all these things. The thing which was nice too is like because I have types, I could actually define a real domain, and with that domain, this helped, this made it more readable, this made it more maintainable, and because I have static typing, suddenly my compiler is my friend, and if I do something dumb, is like it will not compile, and so this is so I'm a happy camper. I have so this is so okay. I have open questions, but I won't talk about them here. So this is me. If you want to talk more about machine learning and this type of topic, I would be happy to talk about this. The repository with the whole code, with the good, the bad, and the ugly, is on James S. Dixon here. And I started to take these ideas and put them into a library, which is alpha-ish. If you also want to talk about this, take a look at Atropos. That's it. And so yeah, that's me. Talk to me afterwards if you want. Thank you.